Okay, good morning, friends. So now we have several more people. Cool. All right, so couple of announcements. Right, so we have our major exam on November 16. I am sure you must have seen the timetable. However, the timetable mentions the time of the exam as 9 to 12, but it is soon going to be changed in our case specifically to 1 to 4 o'clock on the same day. Right, so we did not have a big enough classroom available in this time slot, so therefore the time slot of our exam has been changed. Okay, all right. So I hope you have enjoyed your holidays and now um, you are kind of ready to discuss more about groups. Right. So what did we see about groups so far? We defined this notion of a permutation group and more generally a group. Then we saw the notion of a subgroup. It's a subset of the group which kind of retains the structure of the group within itself. And then we also saw in the last class, what do we mean by cosets of a group, left coset and right coset of a group. And then we saw this theorem called Lagrange's theorem. What does the Lagrange's theorem say? It says that the size of a subgroup, if you have a finite group, then the size of a subgroup of that group is always going to divide the size of the group. Right. Uh, any questions so far, or if there is anything that you want me to repeat, just raise your hand and feel free to tell me. Right, so especially these subgroups and cosets is something we'll need today quite a lot. Okay, fine. So people seem to be remembering whatever we have done so far. Right, so what is the plan for today? The plan for today is to understand the behavior of groups. What do I mean by that? Right, so um, I hope all of you will agree if I say that the behavior of people around us is more important than their appearance, right, or the kind of clothes they wear. Right, so we'll try to separate the behavior of groups from the appearance of the group or the attire of the group today. Okay, so we have already done this for graphs. How did we do that? Does somebody remember? I mean, this is a more like an intuitive question. This is not a formal mathematical question, but yeah. How did we separate the behavior of a graph from the appearance of the graph? Right. So we said that, okay, look, these under certain conditions, the two graphs are really the same person with different clothes. Right. So I'm not sure whether people are getting what I'm hinting at.
Isomorphism.
Isomorphism. Yes. Oh, well, yeah, you're right. Right. So what did we see in case of graph isomorphism? So recall graph isomorphism. What did we say? We say that, okay, two graphs are isomorphic if one the vertex set of one graph can be renamed into the vertex set of another graph in such a way that the adjacency is maintained, right? So maybe something like this. Right. So if I call this A, B, C, D, E, and if I call this 1, 2, 3, 4, 5, I claim that these two are really the same person with different clothes. Why is that? Because if I have a right, so I can construct a bijective mapping between the vertex set of one graph and the vertex set of the other graph in such a way that the adjacency is preserved. And what would be that mapping? Is it possible in this case? I think it should be possible, no? Yeah, I think I need to add one more. No, but oh no, I think I messed up. Okay, so it's apparently it's not possible in this case. Let me just slightly change the graph. Okay, right. So let me put vertex number 2 over here, and these are its neighbors. Right. So how do we construct an isomorphism between these? Right. So you identify that this is a 4 cycle, and here you have a 4 cycle, 1, 3, 4, 5. Right, and maybe you'll try to match those. Right. So basically, A goes to what? 2, then maybe B goes to 1, C goes to 3. What else? E is the neighbor of B, but not a neighbor of C. So 5. E goes to 5 and D goes to 4. This is a graph isomorphism between these two graphs. Okay, so analogously, let's come back to groups. Analogously, let's try to separate the behavior of groups from the appearance of the groups, and we'll do it by defining something called a group isomorphism. Right, so the question again in this case is going to be the following: given two groups, can I rename the members of one group by the members of another group, and can I suitably rename the binary operation of the group in such a way that everything kind of checks out nicely? Okay, so with this intuitive idea, let us see a concrete example of this, and then we'll formally define this term called graph isomorphism. Okay, so here is an example. So I have written down some 3 groups over here. So let us understand them one by one. So the group written in black is the set of symmetries of this flower. We have seen this earlier, right? So we have seen that, okay, if you rotate the flower anticlockwise, let's say through 72 degree, its appearance is not going to change at all. Right, so and there is nothing special about 72 degree. I could also rotate it through 144 degree and whatnot. So this is 3 times 72 degree and this is 4 times 72 degree, whatever that is. And if I don't rotate the flower at all, in either case the flower is going to look identical. Right, so this is the group, and then the star operation is really applying one transformation after the other in some sense, right? And then so basically we have enlisted this explicitly written down the binary operation star on this group, right? So I hope all of you remember we had done that, I think 2 lectures back. So this is the first group. The second group we are going to look at is the green group, which is the numbers modulo 5, right? So 0, 1, 2, 3, 4, and the group operation is addition modulo 5. Right, so it's analogously I have written down the table of this group. Okay, and the third group we are going to look at is the following, right? So consider the set of complex numbers. Look at the complex plane, right? So here is the complex plane on right. So I'm referring to this diagram. So here is the complex plane. Right, so I'm looking at the unit circle on this complex plane, the set of complex numbers having unit modulus, and let me identify the 5th roots of unity on this complex plane. Right, so where are they going to lie? Obviously, 1 is a 5th root of unity. Then there is going to be another guy sitting over here with an argument of 72 degree. There is going to be somebody sitting over here. And there's one root over here, and then there is one root somewhere over here. Right? So I claim that the set of 5th roots of unity under the complex multiplication operation forms a group. Right? And why is that so? I mean, the idea is that multiplying 2 complex numbers with unit norm is just like adding their arguments, right? Adding their arguments modulo 2 pi. Right, so therefore I can simply write e to the 2 pi something times I times e to the 2 pi something else times I as e to the 2 pi something plus something else times I. Right, so that way I have constructed this table, and you can check that this actually forms a group. Right, so now I want to say that although these groups appear completely different, the set of elements in those groups are completely different, these groups have the same structure. Does somebody want to justify the statement? Try and justify the statement. Why am I saying? Yeah.
By a complex number is simply by a unit modulus complex number is just rotation, like. So like if you multiply any complex number by e raised to power 2 pi I by 5, you just rotate it anti-clockwise by an angle of 72 degrees.
I see. So that way you are trying to relate the black group with the orange group. That's fine. But what about
We
the
can
orange group and the green group? Let's say, yeah, Divyansh.
we can construct an isomorphism like between elements such that
Hmm.
if in one group we have f star g some like h element, then in other
Hmm.
like some mapping whatever like a of f star into a of g is equal to a of h. So that's
Ah, yes, you have the right idea. Somebody's hand was also up. Who was that?
So I had the same idea that, like, as in graphs, when two elements are mapped, their result is the mapping of the result of them. Result of the mapping is the result of.
Yeah. And moreover, the mapping must be a bijection,
Yes.
right? That is a requirement. All right. So the answer that people have given is the following. So the idea is the following. So suppose you have two groups, right? So let's call the group something. Let's call the groups G1 and G2 or G and H maybe. So I have two groups G and H. So G has some group operation. Let's call it the square operation. And H has some group operation. Let's call it the diamond operation. Right, so what is the square operation after all? So it's some kind of a black box which will take two elements of this group as input and out comes another element of the group. And similarly the operation diamond over here is another black box which takes two elements of H as input, and once you put them in, the box outputs some element of H once again. Right, and then these operations satisfy certain nice conditions. They are associative, they have an identity element, and then under those operations every element has an inverse and so on. Right, so now what do we want? We want some kind of a function which maps the elements of one group into the elements of the other group. So let me draw that. Right, so we want some kind of a function, let's call it phi, which goes from the set G to the set H, and we want this function to retain the structure of the group. What do I mean by that? So suppose I have some element x over here and some element y over here, right? So what do these get mapped to? They get mapped to fx, and y gets mapped to fy, sorry, phi x and phi y. So let me fix this. Phi y. Right, so what do I want? I want that if I operate this if I operate this square on this binary operation square on x and y, I'll get something. What will that be? That will just be x square y. Okay. Similarly, if I operate the diamond on these two inputs, I'll get something. Okay. What do I want? So okay, 1 6. So what will I get over here? I'll get phi x diamond phi y. Right. So what I want over here is that if I apply the function phi to this x square y, I want to get this guy. Right? And suppose this happens for every xy in the group G. Okay, so then what can I say? Then I can say that this pretty much retains the group H, pretty much retains the structure of the group G. It's just that this X is X, right? So instead of wearing the garment X, you are wearing the garment phi X, and instead of having this group operation square, you are having the group operation diamond. It's everything is just a renaming of something else. Okay, and moreover, we want phi to be bijective. Right, so which means we can kind of go back and forth. Right, so if such a function exists from the set G to the set H, or from the group G to the group H, then we will call the groups to be isomorphic. Okay, so this is the idea. Right, so we are now going to put down the definition of a group isomorphism, but is the idea clear? If it is not, you should definitely raise hands and ask questions right now. Okay, cool. So the idea seems to be clear to everybody. Right. So now what next? We are going to formally define this notion of a group isomorphism, right? So right. So we are going to say that it's a function from one group to the other, which kind of maintains the structure of the group in this manner, and it's a bijective function. Okay. But we will alongside this definition, we are also going to define another notion called a group homomorphism, which is closely related to group isomorphism. Right. So we'll do this together. Okay, but this picture should remain in your mind. Okay, right. So let's put down the definition. Let G square and H diamond be groups and phi going from G to H be a function. Right, so I'm just saying it's a function. I'm not yet saying it's a bijection. Okay, so several definitions in this single definition. We say that phi is called a group homomorphism or simply a homomorphism. We don't have to specify the group homomorphism every time. If for all xy in the domain group, what do we have? Right, so we want that whether we apply the binary operator to x and y and then apply the function phi to the result, or whether we first apply the function phi to both x and y and then apply the binary operator on them, right? So we want an identical result. Right, so mind well, xy are elements of G, so therefore it makes sense to operate the square on them because square is a binary operation on G, whereas phi x and phi y, both of these are elements of H. Right, so we are therefore operating them with the appropriate binary operator, which is the diamond and not the square. Right, so here we are not saying that phi is injective, surjective, nothing. It's some function which satisfies this condition, then it's called a group homomorphism. And now we'll say that if additionally phi is a bijective function, then we'll call it a group isomorphism. Right, so phi is called a group isomorphism if phi is a homomorphism and phi is also bijective. And finally, we'll say that these two groups are isomorphic if there exists an isomorphism between them. Simple, right? So G and H are said to be isomorphic if there exists an isomorphism between them. Okay, and similarly, right, so let me also add a, right, so recall the definition of a graph automorphism. What is a graph automorphism? It's an isomorphism between the vertices of the graph, and it's an isomorphism between the graph and itself. Right, so similarly, we'll define the notion of a group automorphism. Right, so definition: an automorphism of a group is an isomorphism between the group and itself. Right, so this is completely analogous to the notion of graph isomorphism, isomorphic graphs, and graph automorphism. The only thing we have added over here is this notion of a group homomorphism. Right, so the homomorphism merely states that, okay, well, except for the condition that the function must be a bijection, everything is nice if the group structure is kind of maintained. Okay, so let us see a couple of examples. Right, so let us take these two groups which we have seen earlier, the complex fifth roots of unity under multiplication, and then this group Z5 under addition modulo 5. Right, so consider, so example, right, so Z5 under addition modulo 5 and fifth roots of unity under what, multiplication, complex multiplication. Right, so let us try to identify all possible homomorphisms and automorphisms between these groups. Isomorphisms between these groups. Right, so let us focus on what should we focus on? Let us focus on isomorphisms first, or what should we do? Okay, so isomorphisms. Let us focus on isomorphisms. Right, so both these groups have 5 elements. Right, so the number of bijective functions between them is going to be 5 factorial, which is 120. But obviously, we are not going to go and scan each of these bijective functions and test whether it is a group isomorphism. We are smart people. Okay, so we'll do something smarter than that. Right, so let us do in the following way. Right, so right, so Z5, we want a function which goes from Z5, which is 0, 1, 2, 3, 4, to this, let's call this set C5, which is the set of complex fifth roots of unity, which is 1 e to the 2 pi by 5, e to the 4 pi by 5, e to the 6 pi by 5, and e to the 8 pi by 5. That's it. All right, so how do we construct an isomorphism between these groups in a smart manner? Right, so let us try to find, Somilius, go on.
So firstly, we can note that the identity will map to the identity.
Okay, that's an observation. Okay, good.
And
Although we will prove this observation shortly, but yeah, okay, good. Go ahead.
And then if we choose what one maps to, then we have already fixed the whole mapping, because the order of 1 is 5. So like we'll already fix what 2 will go to 3, 3 will go to 1, 4 will go to.
Why do you say that? Could you explain a bit more? You are right, but
let's say 1 maps to x, then 1 plus 1 will map to x into x.
X plus x and so on.
Yes.
X times x and so on.
Yes.
Right. Yes, you're right. Okay, so what Saumil is trying to say is that as soon as we fix what is phi of 1, right, his claim is that we have fixed the entire isomorphism, provided it's an isomorphism. Right, so basically he's trying to say, if as soon as we fix phi of 1, either there is no isomorphism which has this particular value of phi of 1, or there is a unique isomorphism. Right, so let's see why that is so. Right, so suppose I fix phi of 1 to be what? Let's say I fix phi of 1 to be 1. Right, so now remember, the square operation really is addition modulo 5, and the diamond operation is multiplication. Now what will happen? So now what is, so this implies, so then what do you get? So then you'll get phi of 2, which is just phi of 1 plus 1, right? So this is plus, let me make it explicit, 1 plus 1 modulo 5, right? So this I'm going to use a shorthand over here. I'll just write plus with the suffix 5 for plus modulo 5. Right, so then by the definition of right, so this phi is supposed to be a homomorphism in the first place, right, in order to be an isomorphism. So what does this imply? So this must be phi of 1 times phi of 1. But phi of 1 is 1, so then this is also equal to 1. Right, so what does this mean? So it means that if phi of 1 is equal to 1, then phi of 2 is also forced to be equal to 1 in order for phi to be an isomorphism. In order for phi to be a homomorphism. And likewise you can similarly check that phi of 3 is also forced to be 1, and phi of 4 is also forced to be 1. Phi of 0 is also forced to be 1 in this case. Right, so what function are we getting? We are getting a function which maps everything in Z5 to just 1. And this is in fact a group homomorphism. This is a homomorphism, but not isomorphism. Right, why is it not an isomorphism? Because simply because it's not a 1-1 function, it's not injective. Right, so now let us try something else. So this attempt failed, right? Mapping 1 to 1 is a failed attempt. Let's try mapping 1 to something else. Right, so let's say right, so this is attempt 1. Right, so let's do some other attempt 2. Right, so suppose phi of 1 is equal to, let's say, e to the power 4 pi by 5. I'm just picking some arbitrary element and then just trying out what I get out of it. E to the power 4 pi by 5. Right, and so then what will happen? Then by the similar logic, by exactly the same logic, in order for phi to be a homomorphism, what should phi of 2 be? Right, so we are trying to construct an isomorphism. In order for phi to be an isomorphism, it must be a homomorphism in the first place. In order for phi to be a homomorphism, what should phi of 2 be in this case?
E to the power 8 pi by 5.
E to the power 8 pi by 5. Why? Because exactly the same idea. Phi of 1 plus phi 1, which is phi of 1 times phi of 1. Right, so this e to the power 4 pi by 5 times e to the power 4 pi by 5. So that is just e to the power 8 pi by 5. Phi of 3. Somebody? Should I call people randomly in this case? Parth? Right, people have started leaving as soon as I said I'll call people randomly. Okay, I'm not sure whether Parth is attentive. Somebody else, Sarthak?
Sorry, sir, I have not attended previously.
Sir, e to the power 2 pi by 5.
Okay, Sarthak said it must be e to the power 2 pi by 5. Why is it that so? So basically,
Sir, the same logic.
yeah, why is it Sarthak?
Sir, we'll use the same logic, like phi of 3 will be phi of 2 plus 1, and that will be, yes, base 5, and that will be phi of 2 diamond, phi of 2 into phi of 1.
Absolutely. Right, so therefore e to the 8 pi by 5 times e to the 4 pi by 5, so that is e to the what, 12 pi by 5, which is e to the 2 pi by 5. Right, and then similarly phi of 4, right, whichever
Sir,
you know
here
it's,
all of these should have iota, right?
sorry?
Like it should
Oh,
be.
sorry. I missed that completely. Sorry. Right. I messed it up completely. Yeah, so all of these should have I in the exponent. I hope I did not do that earlier. Yeah, everything is okay over here. Good. Right. Right. So let me fix this up quickly before, and in the meanwhile, just try to parse what is happening. Right. So this is 4 pi I by 5, 8 pi I by 5. This is 2 pi I by 5. And yeah, here also I need to fix 2 pi I by 5, 4 pi I. Right. Yeah, thanks for pointing out. So phi of 4 in this case is going to be what? So it's going to be phi of 2 times phi of 2, which is e to the power 8 pi by 5 times e to the power 8 pi I by 5 times e to the power 8 pi I by 5. So that is e to the power 16 pi I by 5, which is nothing but e to the power pi I by 5, 2 pi I by 5. Did I do it correctly or did I mess up? One sec. 8 pi I by 5 is fine. So 8 plus well 12 pi I by 5. Right, so that is 2 pi I by 5, and similarly 16. Sorry, yeah, here I think I messed up. Yeah, this is going to be 6 pi I by 5. E to the power 16 pi I by 5 is just e to the power 6 pi I by 5. Cool. So now you can just completely verify that, right? So this phi is in fact a homomorphism, right? So you'll have to try out all possible combinations and check that this condition is satisfied, right? And in fact, in this case, I think you are getting an isomorphism, right? And okay, finally, I need to add that phi of 0 in this case is going to be phi of 4 times phi of 1, because 4 plus 1 is 0, modulo 5. So that is going to be just going to be e to the power what, 10 pi I by 5, so which is just 1. Right, so this is a homomorphism. In fact, this is an isomorphism. Right, so and obviously this is not the only isomorphism. The more natural isomorphism is in this case is going to be 0 maps to 1, 1 maps to 2 pi I by 5, 2 maps to 4 pi I by 5, and so on. That is another isomorphism. Okay, so therefore, what is the upshot of this? The upshot of this is that these two groups are isomorphic. Right, so Z5 and addition mod 5, comma C5 and multiplication are isomorphic groups. Right, so as an exercise, just identify all possible homomorphisms between these groups. That's not too hard. Okay, so the critical observation is that as soon as you fix, if phi is a homomorphism, as soon as you fix phi of 1, right, as soon as you fix phi of 1, phi of everything else is completely determined, in this case at least, specifically, between these two groups specifically. Okay, so I'll add some exercises in the tutorial sheet related to identifying homomorphism between groups, just so that you have some practice with it. Okay, so I think Soumil claimed that if phi is a homomorphism from one group to another group, then phi of the identity element of the first group must be the identity element of the second group. Right, so apparently he had some intuition behind it. Right, so let us pose that as a question and then try to answer it. Okay, although we have given away the answer already. Right. So question. Let G square and H diamond B groups, let ID suffix G and ID suffix H be their identity elements. And then finally let phi be a homomorphism from G to H. Okay, so then what is phi of the identity element of G? So Saumil, since you claimed that phi of identity element of G must be the identity element of H, could you justify that? Could you try to prove that? Or anybody else, not just Saumil, anybody else who wants to try to prove this.
Sir,
Sarthak?
we write phi of x as phi of x square identity of G, and we write that as phi of x diamond phi of identity of G.
One sec. So you are saying that phi of x, so x is some element of G, I suppose.
Yes. So
Right.
phi of
So phi of x is just phi of x
square.
square identity element of G by definition of identity.
Yes, sir.
Then what?
And for it to be homomorphism, we'll
Hmm.
write this as phi of x diamond phi of identity of G.
Okay.
And since identities are unique, that's why we can claim that phi of identity of G must be identity H.
Right. So you're also writing this phi of x as
Phi of
phi
x.
of x diamond identity of H.
Yes, sir.
Right. And then you're claiming that phi of IDG must be same as IDH.
Yes.
Right. So x can be any arbitrary element of G, right?
Yes, sir.
So so G could be, in principle, G could be an arbitrary group. So I don't even know whether there exists some element X which is different from identity element in the group. G could just be the singleton group which contains the identity element. So why do we bother about an arbitrary X? What you said is completely right. I'm just trying to slightly improve it. Right. So instead of X, let me just pick identity G, no, over here. Right.
Sir.
So I can, yeah. Yes, Sarthak, yes.
Yes, sir. We can take X as identity G only.
Yeah, why not? Okay, so let me turn this question into a lemma and then I'll write down the proof. It's a one-liner proof. So this is a lemma, or let me call it a claim. So claim, right? So these are groups. The IDG and IDH are their identity elements. Phi is a homomorphism from G to H. Then phi of IDG is equal to IDH. Okay, so proof. What is the proof? So as Sarthak correctly said, right, what was the starting point, Sarthak? Once again, IDH diamond phi of IDG, right? This was your starting point. Right, Sarthak? Yeah, I guess so. So this is nothing but phi of IDG, right? Why? Because this is nothing. This is due to definition of identity. So again, by definition of identity, this is phi of what? IDG square IDG. Right, so this is the definition of identity of H, and this is the definition of identity of G over here. Right, so by definition of homomorphism, right? So this is nothing but phi of IDG times right, diamond phi of IDG. Right, so what do we have? Right, we have yeah. So Sarthak, yeah, one problem with your proof is why did you claim that this phi of IDG is nothing but IDH? I still don't get that part. Chinmay?
So like we can multiply by the inverse of phi of
Absolutely,
IDG on.
absolutely. Nice. Right, so remember H is a group. This is an element of H. This is an element of H, right? So therefore it has an inverse in H, right? So let us post multiply both sides by the inverse, and what do we get? Right, so we get IDH diamond, right? So I'm skipping several steps. I'm first post multiplying by inverse and then applying associativity, then applying definition of identity, and so on, right? So out of all that, what will happen is this phi of IDG will get cancelled out from both of these, and what I'll get is right. So let me write this intermediate step: phi of IDH diamond phi of IDG diamond phi of IDG ka inverse is equal to phi of IDG diamond phi of IDG diamond phi of IDG ka inverse. Right, so remember this inverse is under so with respect to the operation diamond and taken in the set H. Right, so basically by associativity I can group these in whatever way I want. So basically these two get cancelled out, right? So this cancels out with this cancels out with this, and then what I get is IDH is equal to phi of IDG. Right, so the identity element of the first group gets mapped to the identity element of the second group. What about the inverses?
Sir,
Yeah.
like I proved it that for any x belonging to G, we had phi of x is equal to phi of x diamond phi of
Oh,
ID.
I see. I see. Yeah. So then your argument is correct, right? So you're not using the argument for an arbitrary single element x. You're saying that for every x something happens.
Yes, sir.
Right, and then you're claiming that therefore ID of G must phi of ID of G must be the identity element of H, right? By saying that okay, a group can have exactly one identity element. Good, yeah, that is good. All right, so my next question is what happens to the inverse, right? So I want to say, right, so if X is an arbitrary element of G, right, so how are these two related? What is phi of X inverse in this case? Yeah, Shamun?
So my question actually it's not related, just an observation.
Yeah,
So,
okay.
I have given any two groups, any two. So we can claim that there is at least one homomorphism between them.
Okay, why?
Sir, could you roll back to the previous slide?
Okay.
Sir, I noticed here in the attempt 1, if we can map all the elements of one group to the identity element of second group, we'll definitely get an
Nice.
homomorphism.
Good observation. Very nice, Shamun. Yes. Right. So Shamun's claim is that given any two groups, there exists at least one homomorphism between them. And what is that homomorphism? Just map everything in the first group to the identity element of the second group. Right. Easy to check that that is a homomorphism. Very nice observation. Okay. So let us come back to the claim that we are trying to make. So my question is the following: X is some element of the group G. Right, so therefore X has an inverse in G by definition of a group. What is phi of X inverse and how is it related to phi of X?
Sir, it is the inverse of phi of x with respect to diamond.
With respect to the diamond operation, right? So that is what you would guess if I told you that okay, these two are kind of related nicely, right? So let us make that claim, and Sarthak is also going to tell us the proof of that.
Yes, sir.
Yeah, one sec. Let me just write it. Moreover, for every x in G, the claim is that phi of x inverse is phi of x ka inverse. Yeah, Sarthak?
Yes, sir. So we'll write identity of H as phi of identity of G,
Hmm.
and we'll
One
write
sec. Yeah, we have that already. Okay.
and we'll write phi of identity of G as phi of x square x inverse.
Acha. Okay, fine. So now you're so this is part one. Okay, let me mark these parts. So this is the first claim, and this is the second claim. So the proof, this is the proof of the first claim, right, up to this point, and this is the proof of the second claim, right? So what are you doing? You're writing IDH is equal to phi of IDG, but I know IDG is x time x square x inverse,
X
right?
square x.
So this is equal to phi of x square operation x inverse. Then what?
Then we'll use definition of homomorphism phi
Right. So
of x
this is
diamond.
definition of inverse in the group G, and now you are using the definition of homomorphism. Right. Go on, Sarthak.
Phi of x diamond phi of x inverse. We'll write diamond, sir.
Oh yeah. One sec. I'll fix that. Right. Okay. Then.
And sir, seeing the most left hand side and most right hand side,
Yeah.
we can
Right. So phi of x diamond phi of x inverse is the identity element. Right. So therefore what? So therefore, and similarly, you can also claim phi of x inverse diamond. Right. So similarly prove that IDH is equal to phi of x inverse diamond phi of x. Right. You instead of writing x square x inverse, you'll have to write x inverse square x, nothing else. Right. So then what do you get out of this? So therefore phi of x inverse is nothing but, so this on the left hand side, the inverse is in the group G, but that is nothing but phi of x ka inverse under the group H.
Yes.
Right. Very nice, Sarthak. Okay. Right. So, and mind well, this holds for all any homomorphism from G to H. Right. Not necessarily for an isomorphism. It holds for any homomorphism, and in particular for isomorphisms also. Questions, comments?
Sir, what do homomorphisms tell us? Like isomorphisms make it seems that they have same structure. Like what is the intuition of a homomorphism?
What is the intuition of an homomorphism? Okay, one sec. Let me just plug up my computer. Right. So what is the intuition of an homomorphism? So in some sense, this is like a subgraph kind of a relationship, I would say. And the reason is going to be clear once we prove a couple of more lemmas. Right. So maybe I would suggest you to just hold on for a while. And maybe towards the end of this class, if you don't understand the intuition behind a homomorphism, ask this question once again. Right. So what we are going to do in the remaining around 40 minutes is prove some nice properties of homomorphism and thereby get a better intuition of what a homomorphism really is. Okay. Should we go ahead? Okay. So, right. So let us draw a little diagram and try to understand right, what does a homomorphism really mean intuitively? right? So suppose we have two groups, let's say G and H. So this is the group G, this is the group H. Right, so this is the identity element of G. And this is the identity element of H. And let's say we have a homomorphism from G to H, say phi. Right, so we already know that IDG must get mapped to IDH. We just proved it. Right, so phi in general need not be a 1-1 onto function. Right, it need not be a 1-1 function, it need not be an onto function. So it could have all sorts of things, right? Multiple people getting mapped to the same guy, or there could be elements of H which are not the images of anybody in G, and so on. Okay, so in general, so the image of this function phi is going to be a subset of the set H, right? So this whole group, if you see what all elements in H it gets mapped to, you are going to see some kind of subset of H in general, and the subset is going to include the identity element, obviously, right? So this is image of phi, right? So all the group kind of gets mapped into this image. Nothing goes outside this image. Okay, so now let us say I have two elements in this image. Let's call them A and B, right? So what does that mean? So it means since A is in the image, there must exist some X over here which gets mapped to A, right? So X gets mapped to A. Such an X must exist because A is in the image. Similarly, because B is in the image, there must be some Y over here which gets mapped to B. Right? So now, does that give any one of you some kind of a clue about what kind of set is this image of phi? Is this right? So I'm claiming that this image of phi is not some arbitrary subset of H. It is some nice, it has some nice structure to it.
Like, is it a subgroup in itself?
Right, right. And why do you say that, Chinmay? You must be having some intuition.
Like, if you take phi and then like the result of operations on these will result back in the ring circle itself. Like if we do phi of x square y, then we'll get phi of x diamond phi of y, and that will be in
A diamond B.
Yes, then that will be in the pink circle itself, so it satisfies all the conditions of the group. Then we can show that inverses also exist by the previous.
Absolutely, absolutely. Nice, nice. You're right. So Chinmay's claim is that this image of phi in fact is a subgroup of H. It's not some arbitrary subset of H, it's in fact a subgroup of H. Why is that so? Right, so if I have some two arbitrary elements A and B in this image of phi, as I said earlier, there must exist some X and Y in G such that X gets mapped to A, Y gets mapped to B. Right, so now because phi is a homomorphism, what should X square Y get mapped to? X square Y should get necessarily mapped to A, should necessarily get mapped to A diamond B. And what does that imply? It implies that if A and B are in the image, then A diamond B is also in the image. Okay. Similarly, Similarly, if let's say A is in the image, which means there is some X which gets mapped to A, what does that also mean, right? So we proved that the inverses get mapped to inverses, right? This statement. This statement. Right? So what does that mean? So if it means that if A is in the image, so X is the pre-image of A, one possible pre-image of A, there could be several. So then the question is, what does X inverse get mapped to? X inverse must get necessarily mapped to the inverse of A in the group H, and therefore the inverse of A must also lie in the image of phi, right? So this is A inverse. Right, so now look at image of phi. What do we have? This identity element lies in the image of phi. If two elements lie in the image of phi, two elements A and B lie in the image of phi, A diamond B also lies in the image of phi. And if some element A lies in the image of phi, its inverse also lies in the image of phi. So what does that mean? So this in fact means that image of phi, right? So so image of phi is, right. So let me state it as a claim. Right. So let G square and H diamond be groups and phi going from G to H be a homomorphism. Right. So then the image of phi is a subgroup of H. Right. So what is the proof? Right. So let us quickly write down the proof. The ideas are already there in the diagram. So proof. Right. So if A, B is in the image are in the image of phi, then there exists X and Y in G such that X diamond, sorry, phi of X is A, phi of Y is G, phi of Y is B. Well, there could be several. I'm just picking one of them arbitrarily. Right. So then what does that imply? So then, because phi is a homomorphism, phi of A square B is phi of A diamond phi of B. Sorry, I think I messed up. Phi of X square Y is nothing but phi of X diamond phi of Y, so which is nothing but A diamond B. Right. So therefore A diamond B is also in the image of phi. Right. Next, what? Phi of IDG is phi of IDH. So therefore, is equal to IDH. So therefore IDH is also in the image of phi. And finally, if A is in image of phi, right? So as before, there exists X in G such that phi of X is equal to A, and then what does that mean? So then phi of X inverse taken with respect to the group G is nothing but A inverse, where this inverse is taken with respect to the group H, right? So thus what do you have? A inverse is also in the image of phi. Right, so take two elements in the image of phi, operate diamond on them, you get another element in the image of phi. The identity element of the group H is already in the image of phi. And finally, take any element in image of phi, take its inverse under the group H. Well, what you get is also in the image of phi. Right, so therefore, image of phi is a subgroup of H. Okay, questions? Okay, so let us identify even more properties, right? So this gives us some intuition, right? So we are really mapping a group G to some subgroup of H. Yeah, which is really the image of the homomorphism phi. Right. So now, right. So this image of the homomorphism phi is really a subgroup of H, which is associated in some sense with the homomorphism phi. Now I want to claim that there is a natural subgroup of G which is also associated with the homomorphism phi. Okay, so let us try to identify that subgroup. Right, so let us copy this picture onto the next slide. Right, and then get rid of the unnecessary things. Right, so we are not interested in the image any longer. I need the identity element though. Okay, so phi is some homomorphism from G to H once again. IDG goes to IDH. Okay, so now what I'm going to look at, okay, is the set of elements which get mapped to this fixed element IDH in the group H. Okay, so I'm going to mark off a subset of G, right? And this subset is defined as this is the set of all elements which get mapped to IDH under phi, right? So all these elements go to IDH. Right, so there could be several, right? The function is not guaranteed to be a one function, so potentially there could be several such elements. Right, so and this set is what I'll call the kernel of the homomorphism phi. Right, so this I'll write down the formal definition, but let's get an intuitive idea first. Right, so this is what I'll call the kernel of phi. Right, what is it? It is the set of all elements of group G which get mapped to the identity element of group H. Any interesting observation about the kernel in this case? Somil?
I think it will be a subgroup of G.
Okay, why?
Because if two elements map to the identity, then their product will also using the property of the homomorphism, and yes, inverses will also lie within the kernel.
Absolutely.
And identity also lies in this kernel.
Absolutely. Yeah. Chinmay, are you saying something? You are unmuted, but I cannot hear you.
No, sir. No, sir. My mistake.
Okay. Good. Right. Yeah, Somil, your hand is still up. Okay, fine. Right. So let's put down a definition. Right, so let phi be a homomorphism from group G to group H. Right, the kernel of phi is defined to be the set. It's denoted by cur of 5. It is the set of all elements x in G such that phi of x is equal to IDH, where IDH is the identity of H. Right, and then Soumil's claim is that this set kernel phi must actually be a subgroup of the group G. Okay, so let's put down that as a claim. Right, so if phi G to H is a homomorphism, then the kernel of phi is a subgroup of G. Right, and the proof is once again equally simple. Right, what is the idea? First of all, we need to prove that if two elements belong to the kernel, then their operated element also belongs to the kernel. And why is that so? Right, so if two elements x and y belong to the kernel, right, so both of them get mapped to the identity element of H. Right, so therefore x, what will happen to x? Right, so what will x square y get mapped to? Okay, so proof: if x and y in kernel of G, kernel of phi, then by definition of kernel, then what do we have? Then phi of x is equal to phi of y is equal to identity element of H. Right, so now what is phi of x squared y? Right, this is nothing but identity element of H, diamond identity element of H, which is nothing but identity element of H. Right, and therefore what does that mean? Therefore x squared y is also so this guy also belongs to the group, also belongs to the set kernel of phi. Moreover, what else? So phi, we have already established that phi of IDG is equal to IDH. So therefore IDG also belongs to the kernel phi. And finally, if x belongs to kernel phi, what does that mean? So then, right, so what is phi of x inverse? Right, so this is nothing but phi of x chi inverse. Right, so this is nothing but IDH chi inverse, which is nothing but IDH. So what does that mean? So this means that therefore x inverse also belongs to kernel phi. Right, so as if two elements belong to the kernel, then their operated element also belongs to the kernel. The identity element of G belongs to the kernel. If some element belongs to the kernel, then its inverse also belongs to the kernel. Right, so what do we have? So therefore kernel phi is a subgroup of G. It's not some arbitrary subset, it's in fact a subgroup of G. Ramanuj?
So if we look at all elements in G which under the homomorphism map to some arbitrary element in capital, let's say small h, then is that something like the left shift or the right shift thing we discussed earlier of the kernel?
Nice. It is. So that is the next thing that we are going to discuss. Left shift, you mean left coset or right coset? Right?
Yeah, that I forgot the name.
What should it be, Ramanu? Should it be the left coset or the right coset, or should it be both?
Both, obviously, because like if
Sorry?
you can get it from the, I mean, if you can, like, for example, ID H, for example, goes some distance left to reach an element h, then it is that much left of the kernel as well, and that much like it goes right somewhere, then it's
right.
that.
So the idea is that the identity element in fact commutes with every element of the group, right? So that is the central idea of what you're trying to say.
Yes. Yeah.
Yeah. Good. Good. Yeah, nice observation. So that is what we are trying to do now. Right. So what essentially Ramanuj said is, well, I would say he raised a question. Right. So he said that, okay, well, we looked at what is the set of elements that get mapped to IDH. So what is so special about IDH? Why not consider some arbitrary element over here and look at the set of elements in the group G that get mapped to this A? What will that set be? Okay. Right. So I hope the question is clear. Right. So I mean, the question is analogous. Just like we asked, what is the set of elements of G that get mapped to this specific element IDH? Then the other question we are trying to ask is, pick some arbitrary element A of the group H. What is the set of elements of G which get mapped to this fixed element A? What does that set look like? And then the guess is that, okay, that in fact is a coset of the group. What kind of coset? Is it a left coset? Is it a right coset? Or is it both? We'll try to figure out.
So it can also be 5, because like if it isn't in the image, then
right. So if A is not in the image of the set, image of the homomorphism phi, then that set is just going to be the empty set. But let's assume that A is in fact in the image of phi. Okay, otherwise the question is not even interesting. Okay. So let us try to analyze that. Right, so let's slightly modify this picture. Right, so let's get back the image of phi over here. Let's say this is the image of phi. And now I'm doing the following task for every element in the image of phi. For every element, I identify the subset of G which gets mapped to that element. In particular, we have already seen that the kernel of phi is the set of elements which gets mapped to IDH. Right. So this guy, everything over here, everything in this set gets mapped to IDH, and this is the kernel of G, kernel of phi, as defined earlier. Right, so let's do it in fact for every element of in the image, and then for every element you'll be able to identify a subset of the domain which gets mapped to that element, right? So maybe this gets mapped to A, maybe all of these get mapped to some B, maybe all of these get mapped to some C, and all of these get mapped to some D. And that's it. So this is the image of phi. Image of phi, let's say, just contains 5 elements. Okay. So let me slightly change the color so that these set boundaries don't get kind of mixed up with the arrows. Okay. Okay, I think there is something on chat. Oh, nothing over here. Okay. Fine. And now let's make a claim. Right. So phi going from G to H is a homomorphism. So for any A in the image of phi, let's say CA be the set of elements of X in G such that phi of X is equal to A. Right, so clearly these CAs are going to partition the set G. Right, that is clear just by, we don't even need to worry about the group structure. We don't even need to worry about whatever, phi being a homomorphism, nothing. Take any arbitrary function from any set to any other set, the set of pre-images of, right? So if you put together pre-images of a given fixed element into a set, and you do this for every element in the image of the function, you're going to get a partition of the domain. This is going to happen for every set. But then in this case, we want to claim that this partition is not some arbitrary partition. In fact, these, right, so all of these are in fact all the cosets of the kernel. Okay, so then what? So then CA is a left as well as a right coset of kernel phi. Moreover, every coset of kernel phi, every whether left or right coset of kernel phi is CA for some A in the image of phi. I mean, what I'm trying to say is these are all the cosets. So this second part is trivial because in fact these sets CA partition the group G, right? So therefore the kernel cannot have any other coset, right? So let us try to just prove that CA is a left as well as right coset of kernel phi. Ramanuj, since you made the claim, do you have an intuition behind the proof? Do you want to suggest a concrete proof maybe?
Wait, I'll have to think about it like for a little bit.
I see. Right. So let me just give a hint. Right. So A is in the image of phi that is given to us. So suppose X is one pre-image of A. Okay, X is one of the several pre-images of A. Right. So let me suppose right. So suppose X in G is such that X is phi of X is equal to A. Yeah, Ramanuj.
Yes, so I thought of a basic structure of the proof. So A is an arbitrary element in the image of G, which is not identity element. And then you take A, so say it is X, A maps to some element X, which is not necessarily unique. Then you say that every element, say X, which like every element, say X, which
let's call it something different. So X is one fixed element which maps to A.
Yeah.
Now you want to say every element Y which, yeah, go on.
So every element in the kernel of G, in the kernel of phi, so psi, whatever. So you multiply X with that element, and then you get another unique element, and which is also a part of the coset in which X is, because when you operate psi on them, then the kernel one gives identity, and the other one will have to give A.
I get your idea. The idea seems correct. It's just that the wording or seems to be a bit messed up. But yeah, yes, you're on the right track, definitely. Right. So what should this right? So what should this set CA be in this case? Let's first guess what CA should be, and then we'll try to prove that CA is in fact that set. Right. So what should we expect CA to be? Right. So we would expect CA to be the coset X square kernel of phi. Right. So we want to prove that CA in fact is the coset X square kernel of phi, and which is also equal to kernel phi square X. Right. So by the way, I'm not in every claim. Maybe I should ideally mention what is the identity of G, what is the identity of H, what is the operation of G, what is the operation of H. But I'm just being consistent with all the previous claims, and I'm just skipping all this. Right. So let us try to prove this. Right. So let us try to at least prove one way that if Y is in CA, then Y must be in this set. Right. So for all Y in G, the following holds. What holds? If Y is in CA, what does that imply? That implies that by definition of CA, that implies phi of Y is equal to A. Right. Now, what does that imply? Right. So that implies that phi of, look at this element. So this is the trick basically. What is phi of Y square X inverse? Right. So that is just phi of Y. Did I do it in the right way? One sec. All right, so let's see what we get out of this. So this is nothing but phi of Y, because phi is a homomorphism. This is nothing but phi of Y diamond phi of X inverse. Right. So phi of Y is nothing but A, and phi of X inverse is nothing but A inverse. So this is A diamond A inverse, which is nothing but IDH. Okay. So now what does that mean? So therefore what? Right. So therefore, by definition, so that implies, sorry, this implies that Y square X inverse belongs to the kernel of H, kernel of phi. By definition of kernel, once again. Right. So now what is Y? So that implies, so remember, Y is nothing but Y square X inverse square X. Right. So what does that imply? So Y square X inverse belongs to kernel of phi. So therefore Y, which is equal to Y square X inverse square X, right? So this guy belongs to the kernel of phi. So this guy must be in the set kernel of phi square X, which is the coset. Right, and then everything is going to hold even in the reverse direction. So it's a easy task to see that, right? So if Y, which is equal to this Y square X inverse square X, is in the kernel of X square X, so all that it means is that, right? So Y square X inverse must be in the kernel, right? So this is some H square X where H is in the kernel, right? So therefore Y square X inverse, which is H, must be in the kernel. Right. So now is this clear or is this too fast? Maybe in the next lecture I'll go over this once again. But for now, let me just finish this. So this holds even in the reverse direction. Now, if y square x inverse is in the kernel, what does that imply? It implies that phi of y square x inverse is the identity element of H. Right. So maybe I should split this. Right. So this implies that phi of y square x inverse is equal to IDH. Right. So now I can safely put a reverse implication. Right. So if y square x inverse is in the kernel, it means that phi of y square x inverse is just the identity element of H. Now, because phi is a homomorphism, all that means is that phi of y diamond phi of x inverse is nothing but IDH. Right, but phi of y, right? So which means that phi of y must be equal to A, because phi of x inverse is just A inverse. Right, so basically, therefore, I can safely put a double implication in everywhere. Right, so therefore, what does that mean? So that means that CA is nothing but this coset kernel phi square H square X. Right, and similarly, you can prove CA is also equal to X square kernel phi. Right, so what will you do instead of considering phi of y diamond phi of x inverse, just consider phi of x inverse diamond phi of y. Nothing, that's it. Okay, so we'll go over this. I understand this was in a bit of a hurry, but we will go over this once again in the next class. And then in the next class, we'll just see some nice implications of whatever little group theory we have studied so far. Rishabh?
So here we had the result that C if H you had curl of phi and we constructed left and right coset from there. So like conversely, I think if you have any group, say K, and its left and right cosets are all equal, then you can construct a homomorphism such that it be a kernel.
Homomorphism into what group?
I think the set of all cosets is your group.
Nice. Yes. That is a valid point, and that is true. In fact, probably we'll not go into that in this course, but maybe I'll I'll make it into a tutorial exercise, add several hints for this, and I'll make you prove that. But yeah, what you said is right. Right. So his point was, if you have this kind of if you have some subgroup of G which has this nice property that every left coset of that subgroup is also a right coset and vice versa, you can actually make it into a kernel of some homomorphism, appropriately constructed homomorphism into some appropriately constructed group. That is true. Okay, yeah, time is up. So we'll meet on Thursday. Chalo, see you. Bye-bye.